Hello and welcome back to Automotech, and in this video, we will show you how does a Tesla electric motor work. The apple of Elon Musk's eye, Tesla Motors has made progress by leaps and bounds to become the leading and most sought-after automobile manufacturers in a short span of just 16 years. It's also the manufacturer of one of the world's fastest vehicles. But how is the ingenious engineering that goes into making these supersonic vehicles a reality? This all will be covered in this video on how does a Tesla electric motor work. Traditional automobiles that work on internal combustion engines, meaning the fuel burns inside the engine, hence the word combustion engine, causing a controlled explosion inside the engine. This releases energy that pushes a series of pistons, which in turn rotate the crankshaft that causes the wheels to move. In contrast, electric vehicles or EVs are automobiles that run on electric motors that are charged from traction battery packs consisting of hundreds of lithium-ion batteries embedded in the base of the vehicle. All EVs are not of the same category though. They're broadly categorized into three types. 1. Hybrid electric vehicles or HEVs. 2. Plug-in hybrid electric vehicles or PHEVs. And 3. All-electric vehicles or AEVs, which are also called battery electric vehicles or BEVs, which will be the center point of this video. As you can guess, hybrids or HEVs are not completely battery-powered. They're still provided with gasoline tanks. However, they do come with an electric motor provision as well that are powered by energy stored in the batteries. The principle behind hybrids is regenerative braking, meaning whenever the user brakes the automobile, the energy that's otherwise lost in conventional automobiles is captured by the electric motor, which doubles up as a generator in this case. While this doesn't make the vehicle completely electric or completely green, it does help reduce fuel costs and emissions to an extent. Second category is plug-in hybrids or PHEVs. These are more worthy of being called hybrids in all honesty because, as the name suggests, they also come with plug-ins charging provisions. The vehicle can be operated solely on batteries, and after the charge depletes, the combustion engines can kick in to save the day. The usual distance a typical PHEV can cover on a completely charged battery is around 45 miles, just over 70 kilometers for the Commonwealth nations. They can also be operated in series or parallel operation modes. In series mode, the electric motors will be used to run the wheels, whereas the gasoline will be used to generate electricity for the motors. And in parallel operation, both the electric motors and the engine can rotate the wheels directly, as both sources will be mechanically coupled. All electric vehicles or battery electric vehicles eliminate the need for gasoline and related provisions such as fuel tanks, pistons, crankshafts, gearboxes, etc. in its entirety. They roll the wheels via electric motors that are powered by a stack of lithium-ion batteries embedded underneath the seats of the vehicle. Before we get into the details on how Tesla manufactures state-of-the-art electric motors for its EVs, we will have to take a trip down memory lane back to your high school physics class. Remember Faraday's law of electromagnetic induction, in which we were taught that rotating a coil inside a magnetic field induces an electromotive force inside the coil. And this very basic fundamental principle is what lies at the heart of almost all EVs and is what makes them a possibility. Now imagine that inside the static magnetic field, you have placed an electromagnet, which is basically a coil that induces magnetism. Meaning it's not magnetic intrinsically, but due to current passing through it, it becomes magnetic in nature. When you place it inside the static magnetic field, whenever the same poles of the static magnet and the electromagnet face each other, they will very obviously repel each other, making the electromagnet complete half a cycle. But the cool part of the electromagnet is that it changes polarity with the current, meaning if the supply of current is stable, the electromagnet will complete the other half cycle as well. And with continuous current supply, the electromagnet will keep rotating inside the static magnetic field. This is the fundamental principle in which rotary components of Teslas and all other EVs are manufactured upon, meaning this is the simple concept behind what makes a Tesla move forward, what makes it run. But what will supply Tesla automobiles with such a large and steady supply of electric current? The answer, a stack of hundreds of lithium-ion batteries embedded in the base of a Tesla vehicle. One of the downsides of which is that it makes a Tesla heavier than a normal vehicle. However, considering that it benefits its user immensely in the form of fuel savings and as a result, reduced carbon emissions, it's a trade-off many are willing to take. Not all is bad about the added weight that comes with a battery stack. However, as the vehicles use current supply from the battery stack to power its rotary parts and not kinetic energy coming from the explosive force such as in a traditional internal combustion engine, means that the Tesla will have fewer moving parts compared to any traditional internal combustion powered vehicle. Almost 10 times less to be exact. That's right, that means an EV doesn't need a gearbox, a crankshaft, or any other additional luggage required to get it moving compared to traditional automobiles. This also translates to near noiseless operation and lowered maintenance costs for the user. Since the batteries are placed at the base of the vehicle, the center of gravity gets substantially lower, which improves handling of the vehicle, turning the disadvantage into another plus point. The EVs are still comparatively lighter than ICE automobiles though, on the whole. As a typical electric motor weighs 6 times less than a normal ICE-powered vehicle, the batteries supply the power needed to run the electric motors that are coupled to the wheels. As the shaft of the motor rotates, the wheels rotate along with it. This provides the user with a true 4-wheel drive experience and keeps performance constant whether the vehicle is being used at high or low speeds. However, the batteries produce only DC, whereas the current necessary to drive the wheels is AC, discovered by the namesake of Tesla Motors, Nikola Tesla. To solve this problem, nifty power electronic circuitry comes into play with DC to AC inverters. Electrical engineers watching this video will be familiar with how these inverters perform switching at fast pace to convert the flatline DC current into AC current necessary to power up and rotate the motor, which in turn drives the wheels moving the vehicle forward. The real icing on the cake in Tesla EVs is its groundbreaking electric motor design. The electric motor in Tesla's new Plaid series is a carbon overwrapped rotor. However, the machines required to fabricate such advanced pieces of electromechanical equipment did not exist. That's why Tesla had to build not only the motor, but also the machinery required to fabricate the motor. For this Herculean feat, Tesla Motors instituted Tesla Grumman Automation. Tesla Grumman Automation was originally established as Grumman Engineering in 1963. Tesla acquired Grumman Engineering in 2017 for $135.3 million, after which it came to be known as Tesla Grumman Automation. Headquartered in Prüm, Germany, Tesla Grumman Automation provides apprenticeships to students of mechanical engineering and robotic automation. They also offer professional training courses in technical product design, CNC operation, IT mechatronics, and industrial electronics. Apart from these valuable contributions to society in the form of training and development of engineering students and technicians, Tesla Grumman Automation also boasts a portfolio of manufacturing machinery for the fabrication of microprocessors, memory chips, airbag sensors, roof seals for vehicles, and lithium-ion batteries. The latest addition to Tesla Grumman Automation's curriculum vitae is the state-of-the-art carbon overwrapped rotor that powers Tesla's EVs. The motor is no less than alien tech. It's light enough to be picked up by a single person at around 31 kg. It's almost 6 times lighter than a common IC engine. Despite this, Tesla's electric motor can reach 18,000 RPM at close to 90% efficiency at any speed. This is a landmark achievement compared to IC engines, who suffer a severe drop in efficiency after 5,000 RPMs, and even at peak efficiency, the rate is only 35%. EVs, on the other hand, can deliver 90% efficiency for most of their operations. While Elon hasn't unveiled much details behind the motor's engineering, however, according to the few details he has provided, fiber is wound over the copper rotor at high tension load. But since copper is a metal and prone to expansion under high temperatures, carbon sleeves are used to keep the rotor compressed. Otherwise, it risks loosening at low temperatures due to differential thermal expansion as it contracts. But how does carbon sleeves help in increasing speed and efficiency of the rotor? The answer is that in traditional motors, the sleeves of the rotor are made from high-strength steels. Steel, being a metal in itself, tends to expand under high temperatures, meaning it'll be unable to effectively compress the rotor under high heat compared to the carbon sleeves. This increase in heat is also detrimental to the magnetic fields being generated, especially in case of steel sleeve compressors for the rotor, as high heat causes misalignment of the magnetic domains of the particles inside the material. This results in a sharp decrease in magnetism. This is especially severe in metal. However, with an innovative carbon sleeve compressor for the copper rotor, this drawback can be mitigated to a large extent. This also translates into a much stronger EM field under high temperatures. This means more constant engine performance and higher RPMs compared to any traditional IC engine. This is because the carbon sleeves stop the rotor from expanding under high heat more consistently and effectively compared to steel sleeves. Musk has made a bold claim in saying that the Tesla sports the world's most advanced electric motor in commercial production and outside of any lab. However, this is not the end. Elon, while keeping his secrets, has teased that he has even more exciting engineering stored for Tesla enthusiasts up ahead as he prepares for the launch of the Tesla Roadster. The next milestone for Tesla engineering decided by Elon is reaching higher torque and increasing RPM with advances in Tesla's electric motor technology. Like what you see? Then don't forget to like the video, hit the subscribe button, and turn on notifications to keep updated about the latest developments in EV technology and sustainable energy solutions.